Hello, my name is Nathaniel Acosta, and this is Lab 2 Projectile Motion. To start with, the purpose of this lab is to demonstrate projectile motion and the effects of drag on the system. To model it, I use glow script simulation, tracker analysis, and graphing. Some physics principles that are here in the lab is Newton's second law of projectile motion. A quick preview of the results is that in the dragless estimated simulation, the distance traveled by the ball was greater due to not being limited by drag. In the drag simulation actual experiment, however, the ball had a flatter curve and did not travel as far as without drag. First of all, the system and some assumptions that we can make out of it. The system is the paper ball and the surroundings are the air and the earth. For simulation purposes, drag is equally distributed across the ball's surface, or in case of the regular simulation without drag, drag is not present at all. The ball also has some initial velocity and starts at an initial height of 1.103 meters. It also starts from x equals 0. And the negative x direction is to the left and the positive y direction is up. This is the original video. As you can see, the ball is first thrown in the positive y and negative x direction with some initial velocity in the positive y and negative x direction. Continues that direction until it reaches the peak of the arc, after which the velocity becomes in the negative y and negative x direction. The ball then continues until it hits the ground at y equals 0. This is the tracker video, which is the same exact video except plotted using points of mass to track the position of the ball and get the velocity and the position from that. As you can see, this calibration stick, we used a meter stick to scale, and this is the axes with x equals 0 starting right here where he begins to throw the ball, and y equals 0 right here where it hits the ground. So the first thing is the no drag simulation. There are a few initial conditions for the no drag simulation that we can see. The first is that the only force is the gravity force, which is acting only in the y direction, and that means that we know that there is going to be a constant velocity in the x direction, as you can see here in this bottom left graph. Another thing is that the density of the ball is equally spread, which means that the center of mass is at the center of the ball. Our initial position is 1.103 in the y direction, meters, and our velocity is negative 3.6 meters in the x direction and 3.8 meters in the y direction. And that was taken from tracker using the first two values to ensure that it's the most accurate without drag. The final conditions is that the ball traveled negative 3.384 meters in the x direction, and because the left is the negative direction, this is 3.384 meters to the left. These are some graphs that I collected to show what might be happening to the ball. The first on the left is the x. As you can see, the x scales linearly, which makes sense because there's no force acting in the x direction. The y, however, is a parabola shape, and that's because the force of gravity is acting on it, as you can see from this velocity bottom right graph for y. The next simulation is the drag simulation. The initial conditions for this is the same exact ones, except that we have a drag force acting in both the x and the y direction, and x opposite to the velocity, which means that we cannot say that the velocity of x is constant anymore. The b constant was 0.002 for the drag force, and here's the equation. We had the same exact initial conditions, and the final condition was much less with negative 1.84, and these are the graphs same as well. As you can see, now x is a parabola, or at least a curve as well, and it doesn't scale linearly anymore. And this is the code, and this is the calculation for the drag force. For the calculations for the tracker, once again, initial position and initial velocity is the same. This is from tracker yet again, and we can say that air resistance has some effect on the velocity of the ball acting in the opposite direction of motion, and that the gravity results in the negative y acceleration. Here is the plotted points from tracker, and our initial or final position was negative 1.81 in the x direction. So this is all of the x directions plotted onto a graph, and this green one here is without drag, the simulated one. The orange one is with drag, the simulated one, and these blue dots are the experimental one. And as you can see, the experimental without drag goes far and away from anything else. The orange one, the drag simulated, is much closer to the actual, and this is because the x direction in the simulated is linearly because there's nothing acting against it, but with the other two there's going to be drag acting against it in the x. The y is a lot closer because y only has gravity acting against it, but In the other two simulations, it also has drag. So the drag is still more accurate, I would say, at least in the ending spot, compared to without drag. So I would say that with drag, it's a much closer approximation than without. The overall conclusion, and this is the overall trajectories of both of them, is that you can see that the experimental without drag went much farther than the other one, and the other two just is much more accurate with drag. So possible errors of this is that due to the method of finding the coefficient of drag, it may be inaccurate compared to actually calculating the b-value because it was estimated by plugging in, essentially. And the drag was assuming to have been equally spread against the ball surface, but this could not be true because of the different edges and angles of the paper ball. So a few questions to answer for the end of lab is that because of the short time frame of the simulations, I did not reach terminal velocity in either of them. However, the trend was visible in the drag simulation as the velocity increases and the drag force increases, at some point canceling out to the other. With a higher time frame, a terminal velocity could easily be reached. And if the object was thrown straight up instead of to the side, then the object would reach the floor at the same exact time because the only change would be the x direction. And a projectile motion, the x direction, has no effect on the time the projectile stays in motion. And this can be proven through a kinematic equation just by changing out the y, setting it to the y and the x direction. And if you change the force into the x direction, it has no effect on the delta t. Thank you.